Okay, so the way an atom is arranged is it has a nucleus with protons and neutrons in its center. The protons are fixed. It says what element it's going to be. Neutrons, actually there's some logic to different isotopic forms that an atom can have. But neutrons can kind of come and go. Together, the protons plus the neutrons make up the mass of an atom, okay? And actually, if you add protons plus neutrons, you get the mass number. So actually, we can have the same element with different mass numbers, okay? And that gives us isotopes, okay? So they have different mass numbers. They weigh differently because they have different numbers of neutrons in their centers, in their nuclei. Okay, so for each box, there's a whole number. Yeah.
Sorry, I have a question.
Uh-huh.
On some of those, it says that there's only, some of them only have one, some of them have two, and some of them have three or more.
Uh-huh.
Is the list that they give, is
Complete?
that exhaustive?
No.
Okay.
No. Yeah.
Like, well then, what about the others?
Right.
Okay.
Yeah, it's not exhaustive. Just kind of a handful of elements that fit that category. One isotopic form, though, seems weird to me because when you say isotope, I'm looking for a second one. But yeah, but I'm pretty sure that that's how that goes. Yeah. Have you guys seen these plastic quick study things for like? There's one for chemistry, one for biology, one for geography. The quick study laminated sheets. There's one for chemistry, and there's different ones for chemistry. But one of them had like, for the elements, the different isotopes for that element. So it's kind of fun. Those plastic sheet things you get at the. Anything so. So in the periodic table, it will give for each element as a box, and it gives you the symbol for the element, and it will give you the whole number, which is the atomic number, the number of protons. It will also give you a decimal number, and that decimal number is the average atomic weight of an atom of that type of element. We just call it the decimal number. Okay, and you don't have to memorize either atomic number or obviously average atomic weight for any elements. So, but that decimal number says how much an atom of that type of element weighs. The units are atomic mass units, which we've run into before, AMUs, or the little symbol U for AMUs. Average atomic weight, average atomic mass, atomic weight, atomic mass, those are all kind of synonyms. Anything else? Yep. So we're going to do, it's a classic sort of problem. We're going to, actually, you guys are going to come up with that decimal number. You're going to come up with how do we report how much an atom of that type of element weighs if Mother Nature throws us a curve and there are different isotopic forms of that element. How do you come up with one decimal number, one average atomic weight? And actually it's what we call a weighted average. You're familiar with weighted averages, I know, in all that you do. Like, for instance, in a course, in this class, your homework is worth 10% of your overall course grade. I mean, it's weighted 10%, okay? So that means, well, that's what that means, okay? We can't count it any more or any less. That's what it brings to the table. When we come up with how much, when we come up with a weighted average for an element, we need to take into consideration the abundances, how much there is of each isotopic form. Do a little bit of math, okay, and come up with a weighted average. I'll show you how that works. Okay, so before we get to that, again with average atomic weight, average atomic mass. We use the AMU, atomic mass unit. Again, you'll see me kind of slip back and forth between U and AMU. But it needs to go back to be described as something. And if we take the element carbon, one isotopic form of carbon has a mass number of 12. If you have one atom of carbon 12, it weighs exactly 12 atomic mass units. But there are times when we definitely need to scale up an atomic mass unit. So in terms of grams, an atomic mass unit is 1.661 times 10 to the negative 24th grams. 1 AMU, and that's approximate. 1 AMU is approximately equal to that fraction of a gram. If you have 1 gram of material, in terms of AMUs, that's 6.022 times 10 to the 23rd AMUs. And for some of you, you're like, oh, well, that's a mole. And we'll talk more about Avogadro's number, okay? But yes, that is Avogadro's number. And that's not on accident. So here then, with regard to mass, you have equivalency statements that you can use to get back and forth between AMUs and grams. By the way, the inverse, or 1 over 1.661 times 10 to the minus 24th is 6.022 times 10 to the 23rd. If you divide, it's kind of how that works. They're the inverse of each other. All right. So, in order to come up with that decimal number, you're going to have to be given abundance information about the isotopes. Okay, so when you're given abundance information about a particular isotopic form, what they've done is basically gather a bunch of, for instance, we're going to be dealing with copper. They gather, they accurately, statistically use sound methods to get a copper sample. A natural copper sample. The number of copper atoms goes down there, okay? Then what they do is break it up into its different isotopic forms. So the percent abundance of one isotope, you take the number of atoms of that particular isotope divided by the total number of atoms in the mixture. And then to get it parts per 100, you multiply by 100. The formula I'm going to show you in a minute doesn't have percent abundance, but it has fractional abundance. So here kind of, I don't think you guys might have this, but if you want to underneath it, maybe you do. Oops. There he is. Must be coming up. I'll tell you what I was going to tell you. Fractional abundance for an isotope is equal to percent abundance divided by 100. Okay, so that's fractional abundance. Percent abundance, sorry. Yeah. Okay. So if we pick on copper, remember we talked, or you guys did some homework, where this number is the mass number, right? So we have 2 isotopic forms of copper, one mass number 63 and one mass number 65. And let's say that we know that the copper 63 is abundant almost 70%, 69.09%. The copper 65 is less abundant. It's only 30.91%. Okay? The other thing, well, before I go. So in other words, if we had 10,000 copper atoms, you can move the decimal place over a couple of places, and that means that 6,909 of them would be copper 63, and 3,091 of them would be copper 65. So that's kind of what that means. Okay, so on with kind of switching gears. That was copper. Hydrogen actually has 2 naturally occurring isotopes. I think I mentioned this deuterium the other day. Okay. It has a 3rd isotope called tritium, which is not abundant in nature. So here we have hydrogen with a mass number of 1, mass number of 2, mass number of 3. Now, hydrogen is the simplest atom, lightest atom on the periodic table. Hydrogen's atomic number 1, so it means it has 1 proton in its nucleus. So can you see where regular hydrogen has 1 proton and no neutrons? Okay. Mass number 2 has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. So, one of the things in order to come up with a weighted average is we need to know for each isotope how much it weighs. So here are the masses for an atom of each of those isotopes of hydrogen. And then over here, that last column is, in nature, what's their relative percent abundances. So you can see that, my goodness, the regular hydrogen is far more abundant than the deuterium, and the tritium, it's not on the radar at all.
I'm guessing is tritium man-made?
Yes.
Okay, I was just assuming, considering if it occurs 0% of times in nature.
I need to check that. If it's not man-made, then if it's off the scale, it's even less than the percentage that are reflected with those big things.
0.0000.
Very rare. So the decimal number for hydrogen is this, and 1.00794 atomic mass units is the average atomic weight for hydrogen. The way they get that number, I'm going to show you how we do this. It's a little process, but this is what you'll see on the periodic table, and that number actually came from these numbers. How abundant each one was and how much it weighed. Okay. The next one on here is boron. There are 2 isotopic forms of boron. Boron has 5 protons in its nucleus, atomic number 5, so it looks like we have 5 and 6 neutrons. That's how much it weighs. There's the relative abundances. Now in this case, before we look at the decimal number for boron, can you see where there's a lot more of this heavier boron, 80-20? Okay, so you figure then, when it comes time to come up with a weighted average, it's going to be closer to the heavier one than it is to the lighter one. And again, we're going to show you how you can use these numbers to come up with that number. Neon, 3 isotopic forms. You can see now in this case, the lightest one, neon 20, has 90% of the naturally occurring neon is that kind. And so actually not so surprising then, the weighted average is closer to that one. And last but not least, magnesium, 3 isotopic forms. So, if you're a visual person, fluorine has no isotopes, so they're all red, okay? Here we have chlorine, 2 isotopic forms of chlorine. Notice there are a bunch more of the red ones. That would be this 75.77%. Fewer of the blue ones. Okay, that would be the chlorine 37, magnesium, and lead. So just kind of a visual sort of thing. All right. So the average atomic weight is, we go ahead and do a summation. So that's the sigma part of it. And the thing that we sum actually is the product of 2 terms. So for each isotope you have to visit its how much it weighs and its fractional abundance. For each isotope, how much it weighs and its fractional abundance. And then you add those together. Okay? And here's where I say what I told you a little bit ago, fractional abundance. You're usually given percent abundance. To get to fractional abundance, we're going to take the percent divided by 100. It's a weighted average. So we're going to pick on copper. So remember, copper was like a 70-30% relative abundance. And here now, that last column, you see how much each of those forms of each of those atoms weigh. Okay, so these are how much they weigh. So does this make sense when we come up with our weighted average? Since this is more abundant, this one, you would expect the answer to be kind of closer to the 62.930 than the 64.928. Just eyeballing it. So what is the average atomic weight of copper? So we're going to apply that summation. We're going to apply this to that little table we saw. So for the first isotopic form of copper, we take its weight of 62.930 AMUs times its fractional abundance, which is 69.09 divided by 100. And then here comes the summation part. We only have to have two terms added together. So then we look at the second isotopic form, and it weighs 64.928 AMUs times its fractional abundance, 30.91 divided by 100. Now, I know that I'm all about rounding to the correct number of significant figures or decimals that you're allowed. According to uncertainty, we kind of talked about how uncertainty propagates the problem. But I'm here to tell you this sort of problem, you're going to round to 2 decimals, and actually this is how the uncertainty usually propagates through. So round this sort of problem to 2 decimals unless the atom weighs less than 10 AMUs. So if the atom weighs less than 10 AMUs, in this case, go with 3 decimals. So 3 decimals for the light atoms. So I think the breaking point is about beryllium. Yeah, beryllium average atomic weight is 9.012182. Boron is 10.811. Okay, so the first 4 you go with 3 decimals. Okay, so then when you do this, you should get 63.55 is the average atomic weight for this element based upon that isotopic information, how much each isotope weighs and how abundant it is. So this sort of problem, and you guys are going to do 2 problems this weekend somewhere in there, fit it in your wonderful weekends, that's going to be due on Wednesday, you can always check your answers. So, because you're going to have a periodic table. So we can find copper. Okay, now every once in a while it'll be a little bit different, but the decimal number up here is 63.546. So you can always check these answers. Oops. All right. So this is kind of what I was describing, kind of eyeballing it. We said that the copper, if we were going to do the simple average, not a weighted average, but a simple average, would be to add the 2 weights together, which is about 63 AMUs and about 65 AMUs, and divide by 2, and we get 64. That would be a simple average. But like I said, this one's much more abundant in nature. So it's going to be tipped more that. And 63.55 definitely is that way. Hydrogen is even more extreme because, like, goodness, the normal hydrogen's like 99 point something % relative abundance. So a simple average of regular hydrogen and deuterium, you add 1 AMU plus 2 AMUs and divide by 2 and you get about 1.5. That's a simple average. But the decimal number for hydrogen is 1.008 or thereabouts. To 3 decimals, it is 1.008. AMUs is what it weighs, average atomic weight, because it's like 99% this. So these will be due on Wednesday, and take a look at them right quick. Don't have them. I don't have a whole lot to add. If you're like me, what gets hard in looking at these problems is matching up the percent, okay, with the isotope. So looks like we have magnesium and chromium, so you can check your answers. So one of the things that I did, and I don't know if you'd have to do this, but like I said, my eyes start to get crossed when I read that sentence that has, for the 3 isotopic forms of magnesium, what is their weight and what's their percent abundance. So actually, I pulled it out right here, and it's just easier to look at. It depends on if I'm in a hurry or not. But all I did was to pull that out of the paragraph. So you're basically going to take, the weight times the percent abundance divided by 100 plus this weight times this percent abundance divided by 100 plus, so you have 3 terms, the product of 3 terms added together. It says don't forget to check your answer with the periodic table. And so 44 is the same thing, very similar. So here's where, like, if a student really wants to be a smart aleck, don't show your work, you just basically go to the periodic table and write down the answer. So that won't work. Any questions about that? Okay, so we're ready to go on to, actually, part 7. I know there's a few slides there, but those few slides just kind of go back to, we're fine, we don't need those few slides. Okay, so let's just do a few slides here.
Yay, a mole.
Yay, a mole.
Yay, moles.
Yep. So, as some of you might already be kind of familiar, a mole is a big number. And the reason we introduce a mole, this big number, Avogadro's number, 6.022 times 10 to the 23rd, which is the same number of AMUs in 1 gram, right? Okay. That number there is Avogadro's number, and it represents a mole. So by definition, you have a mole of carbon atoms if you have exactly 12 grams of carbon-12 atoms, one particular isotopic form of carbon. But I'm going to show you how we really could not possibly count those carbon atoms. It's not practical. It's hard to see them, plus it's just not practical to count a mole. Literally count them. So 6.022 times 10 raised to the 23rd power is Avogadro's number. And it's one of my favorite abbreviations because the abbreviation for MOLE is MOL. All right then.
It's too hard.
Yeah, it's too hard to put the E in there.
Abbreviation for mole is mole.
Yes. So a mole is kind of similar to a dozen. So if you have a dozen of anything, you have 12 things. And if you have a gross of anything, you have 144 things. And if you have a mole of anything, you have 6.022 times 10 to the 23rd of those things. It's a big number. So here I have, and I got these off the internet, so a while back. So rice grains are pretty darn small, okay? If you had a mole of rice grains, you'd be in trouble because the land area on the earth would be covered up to a depth of 75 meters. Just a mole of rice grains. Again, with the rice grains, as important as rice is a staple in many cultures, not a mole of rice grains have been grown since the beginning of time. Again, with the rice grains. If you were to gather a mole of rice grains together and put it in a cube, it would be about 120 miles on length, width, and height. Now with the marshmallows, this one reminds me of the Stay Puft, like with Ghostbusters. If you had a mole of marshmallows, again, you'd be in trouble, because the United States, if you confine it to our country, we would be up to 600 miles in marshmallows. Now with snowflakes, right? Okay, this must have skipped. So snowflakes, think wintertime here in Iowa. A mole of snowflakes would cover the United States up to 2/3 of a mile. See, I said it's hard to count it because, like, if you wanted to get a bunch of people together to count a mole's worth of 1, 2, 3, 4, 5, 6, 7, you would take 51,000 Earths full of people, counting a rate of 1 per second, 75 years to count one mole of objects. I don't know why you'd like to do that, but. And here is a computer doing the heavy lifting here. So take a fast computer, and it does 1,000 millions of instructions per second. The same computer that we're going to task with counting a mole, going through a mole iterations, can count the population of the United States in less than a second, but it would require 1.9 million years to have that same computer go through a mole's worth of cycles. Hockey pucks, a mole of hockey pucks would be equal mass to the moon. Basketballs would be the volume of the Earth. And pennies. A lot of us just like throw our pennies away, you know, vacuum them up, whatever, right? But if you had a mole of pennies, and at the time this was written, the population was such that you took that mole of pennies and you divided it amongst everybody on Earth. Everybody on Earth would get 1.5 times 10 to the 14th pennies. Like, all right, move the decimal place over. That's a lot of cash. So people could spend their pennies at a rate of $1 million a day, okay, and even at $1 million a day, it would take 4,000 years to use up their.
$1 million a day.
Yeah. Good.
However,
the problem is, you can all smell the copper. The problem is that a mole of pennies is problematic because it covers the land area of the Earth up to a depth of 420 meters. So you're like, oh my goodness.
So you would be the richest person on Earth.
That's right.
everyone's super rich and dead.
Yes. Oh, by the way. Yep. So, exactly. So enough of that silliness. Okay. So atoms are very small, thank goodness to us. Now, if you see, for water, if you take about 10 milliliters of water, which is kind of maybe a little bit bigger than the volume of a finger, that is a mole of water molecules. So just to kind of put things in perspective. So we use the concept of a mole for molecules and atoms. It works really well. So 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. So we can take any equality, like that is, and make 2 conversion factors. And they are the flip or the inverse of each other. And we can do problems with them. So we're going to do one problem today. Well, a pair of problems, one type of problem. So we're going to knock these both out. The first one is how many moles. Now the thing in brackets is something that probably won't be there when I get rolling. We could say how many moles of atoms is 1 trillion hydrogen atoms, or we could just say how many moles is 1 trillion hydrogen atoms. It's the same thing. Okay? The thing in the brackets probably will be pulled out. I don't really like this problem in that the thing you're going to start with is 1 trillion hydrogen atoms. You're like, well, what's the what's the uncertainty there, you know? And I think the way I do it on the problem, one of these days I need to change that, is I just say 1 times 10 to the 12th, 1 trillion. So basically, we're going to take 1 trillion hydrogen atoms, and we're going to convert it to moles using one of those two ratios. So that's an atoms to moles problem. The second problem we're going to do is how many atoms is 0.555 moles, or moles of atoms. How many atoms is 0.555 moles? So this one is going to be, we're going to start with 0.555 moles, and we're going to go to atoms. And again, just use the ratio that is going to do the job. So here we go. So the first term in the first one is going to be 1 trillion over 1. Again, I'm not real thrilled with this. Actually, it should say, I think should say 1 times 10 to the 12th. That just looks like a naked number. 1 times 10 to the 12th, that's 1 trillion hydrogen atoms over 1. We want hydrogen atoms to cancel and be left with moles. So does it seem like we need to put 1 mole over 6.022 times 10 to the 23rd atoms? Does that seem right? So this is where you're going to want to make sure that your calculator crunches this and it crunches it correctly. So this problem is not very good. We're going to assume, I can't remember what I assume. We're going to assume that that 1 trillion atoms is exact, and we're going to round according to Avogadro's 4 sig figs. So that's why I gave it 4 significant figures. Usually they're more obvious than this. Did everybody get that, or not quite? And rounding to 3 sig figs, we get 3.34 times 10 to the 23rd atoms. What do you think? Okay. Very good. Well, I don't have a lot. I'm not going to get to the assignment slide, but I did want to send home something for you. I printed these out, so I can't decide. Do you guys want to just wait for me to run to the printer and get them, or do you just want to write it down or get it off a Twitter feed? Because we're done for the day. This was the last thing I want to do. And we're going to pick up here on Wednesday. So I'll tell you, I'm going to go to, this is, you can write down this assignment. Like I said, I'm also going to post it. I'm also going to go get those off the copier. So you guys can wait around, or you can leave. Leave!